It's a pleasure to be here. Thanks. I know Friday afternoon talk on yawning. That's tough. So I'm really pleased with the turnout, and I'll try to make it worth your while. So to get into this discussion on yawning, how's my voice for people in the back? Okay. Okay. Excellent. I'm interested. I became interested in yawning as an undergraduate, as Omar indicated, just because it struck me at the time that this ubiquitous behavior that all of us do multiple times a day, every single day of our lives, and it's not just a human phenomenon, it occurs in other vertebrate species, we don't know why we do it. So that was just like, really? Are you serious? And there's this tremendous lack of understanding regarding yawning. It has this social stigma as well. Yawning in the presence of others is often considered a sign of boredom and disrespect. I don't know how many people are familiar with this, but a few years back, this became pretty widely recognized in the news. A Cornell professor had an outburst because somebody yawned during his lecture. And I guess it was an audible yawn. And he didn't realize that the lecture was being recorded. And he just went off on the class and demanded to know the identity of the yawner.
Yawn outside. Stay out of class. Whatever it is you need to do to get over it. I want to know why 220 other people in this room don't find the need to do that.
He was released and he had to apologize, but during his tirade, he indicated, if you're going to yawn, yawn outside. And this line of T-shirts actually was created after this as well. So it was a major event, and it's not uncommon for people to have experiences where they receive negative social feedback for yawning, something that's involuntary that they can't control, and I find that really interesting. So this is pretty bad, but this is worse. This is a real case where an individual, Clifton Williams, his identity's there, was given the maximum penalty of contempt of court for yawning in a courtroom during a procedure or during a sentencing of his cousin. He attended the sentence, and apparently he yawned during the session, and the judge gave him 6 months in prison for yawning. I'd consider this a complete lack of understanding, and I can't comprehend these types of outcomes. But they're interesting. To complicate this picture a little bit more, Apollo Ono is one of the most celebrated U.S. Olympians, an 8-time Olympic medalist. Apollo Ono is he was a speed skater, the best in U.S. history, but he's also really well known for his excessive yawning bouts leading up to competition. Now it's hard to argue that Apollo Ono is bored or disinterested right before some of the biggest races of his life, right? So this response that Apollo is having cannot be attributed in the same way that yawning is and carries this type of social stigma. He can't control this. This is a response that deserves further attention, I'd argue. So, operational definitions are always good for talks. Yawning can be defined by the involuntary and powerful gaping of the jaw with deep inspiration, followed by a temporary peak of peak muscle contraction of the mandible, and a passive closure of the jaw during the expiration. And this sequence image was taken by one of my collaborators, an undergraduate at the time, at the San Diego Zoo. He actually caught this live of a male orangutan, a peak yawn, showing that first phase of this definition, and then that second phase. It's beautiful. It's highly stereotyped. We can appreciate this in our own actions. Yawning this definition applies more or less to all species that show the response. So if you haven't figured out already, I'm going to be talking about yawning a lot. And I'm not, I realize that yawning is contagious. So believe me, I will no shape or form be insulted whatsoever if you yawn during my presentation. I won't take offense to it at all. Okay, it's a natural response. And in fact, to help initiate things here, I've got a video. It happens to be of myself. It's the only video I could get to play on this PowerPoint. But just to show you that I'm not going to be offended, I'm going to try and induce some yawns right now. All right. So if that didn't make you yawn, maybe you'll feel the urge later, and feel free to let it out. I mean, if you feel uncomfortable, you can cover your mouth, but you know, I don't care. So as I mentioned before, yawning is this ubiquitous response, stereotyped action pattern. It's been documented or observed in all classes of vertebrates. It hasn't been extensively studied in all of these species here, but has been documented. Okay, and it takes on this really highly stereotyped action pattern. Darwin even talked about yawning when formulating his theories of evolution. In his notes, he writes, "Seeing a dog and horse and man yawn makes me feel how much all animals are built on one structure." So as he was formulating the theory of evolution by natural selection, he was recognizing the conservation of traits, and yawning appears to fit one of these highly conserved behavioral responses. If we look at you know, the evolution or phylogeny of yawning, we can't say for certain when it ultimately evolved, but it appears to have evolved with the first jawed fishes. And subsequently, we see this action pattern, at least similar mandibular gaping patterns. Whether they're going to be classified as yawning or not, again, deserves further attention. But we see this in all 5 classes of vertebrates. So it appears to be an evolutionarily conserved response, which supports the view that it has an adaptive function. Now, there are 2 types of yawns. Right? We have yawns that we refer to as spontaneous yawns. These are yawns that are not socially elicited. These are yawns that you would have experience in the early morning hours or the late evening hours. They're physiologically controlled. We see these are fairly widespread. They occur in isolated, non-social species. They occur very early on. Okay, yawning can be observed in utero through ultrasound. And it's earliest documented at 11 weeks in utero. And it appears to be a fairly universal act. If a species shows mandibular gaping patterns like yawning, all members of the species demonstrate that trait. So this appears to be the primitive form of this behavior. But of course, as I've already alluded to and talked about, yawning can also be contagious, right? Socially elicited. This, so far, is limited to only a few highly social species, which I'll speak to this at the end. It doesn't occur as early. It only begins after some period in the juvenile period of maturation, and there's also a lot of individual variability in contagious yawning. So not everyone is equally susceptible to yawn contagion, which makes this interesting. And ultimately, these points suggest that this is a derived feature of this more primitive form of spontaneous yawning. So, I'm very interested. I take an evolutionary perspective to behavior, studying humans and non-human animals, and I'm very interested in yawning and its potential adaptive functions. And there's no shortage of hypotheses about the adaptive function of yawning. In fact, an influential review paper in 1999 kind of cataloged all of the various hypotheses that had been proposed to that point, and this list would be even longer if we would include the last 20 years of some new ones. Speaking to this list, however, there's very little evidence supporting these hypotheses. There's not necessarily evidence falsifying them. Some there is, but there's not a lot of empirical, scientific-driven work to test these hypotheses, and therefore they don't have empirical support. Okay? And again, I found this really interesting, so I began to pursue this question, what might be the ultimate function of yawning? And right now there are 2 distinct camps of perspective and thought about yawning. One is focused on a communicative function, a signaling value that yawning might serve to conspecifics, or members of a species. So individuals might detect yawns in others, and that might provide information about the internal states of group members. other conspecifics. Okay, so it may have communicative value. But this fails to take into account yawns that are occurring in solitary species and yawns that occur among individuals that are by themselves. And it fails to recognize that the yawning likely has some driving underlying physiological trigger. So the second camp of thought is focused on, well, what are the physiological effects of yawning? Right? What causes this response to initiate? What are some factors that modulate it related to our internal states? And these hypotheses basically focus on how yawning might counteract deviations in thermal or in physiological change or facilitate changes in mental state or arousal. And I began to focus on these ideas, the physiological function. So, if yawning serves as some sort of physiological function, it's important to recognize the locality of the yawn. If we look at this motor action pattern, this gaping of the jaw, it's going to have significant circulatory and physiological effects that are relatively localized to the skull. And therefore, it should have impacts on neurophysiology, okay, brain changes. So I began to think about this question a lot. And I was interested in, although there is this stereotyped action pattern of yawns across species, not all yawns are the same, right? And there are differences, or interspecies differences in yawning, as well as intra-specific differences in yawning. Not all yawns are the same. And I basically suggested that if there are neurophysiological effects of yawns from yawning, those changes that are produced from the action pattern should be tied to the magnitude of that response. So in other words, if yawning serves some neurophysiological function, I predicted on a comparative perspective, animals with larger and more complex brains should show longer and more robust yawns. Okay, it's a hypothesis that's basically targeting the idea that yawning would serve a neurophysiological function. If it does, we would expect that it should be tied to differences, interspecies differences in neural tissue. Okay? So I examined this, and I had the basic premise was, let's try and find and acquire as much data as we can on interspecies yawn duration, the magnitude or length of yawns across different species, and then just correlate that with differences in brain size and complexity across species. Are there correlations, positive correlations? So I just took standard data set that had been previously published that cataloged the brain weight, encephalization quotient, which takes into account brain to body mass index, and as well as available data at the time on the number of neurons, cortical neurons across species. And from this list, I instructed some research assistants to just use our publicly available videos online from Google Videos and YouTube, and to find as many species on that list as they could yawning, and to find as many yawns as they could to get representative values from each species. So therefore we acquired average yawn durations from chimpanzees and other species on this list, and then ran some correlations with those neurological parameters. And in total, this sample included 186 yawns from 109 different individuals across 19 species on that list. And here's what we found. Really, really striking positive correlations between the length of yawns between species and the size of the brain. Now, if we look at the longest yawns on this list, humans have the longest yawns in this sample. And this outlying species here with this incredibly large brain are African elephants that were on the sample. They have nearly yawns that are equal in length. We don't have a variability measure there because I had to acquire this data from an individual studying these species in a different study, and didn't have the individual figures. This relationship holds true when we control for body size, looking at encephalization quotient. There's still a positive correlation here. I should mention that the black circles are primates, in the sample. And the white circles are non-primate species. So primates on average have larger brains and also longer yawns. And if we look at the correlation between cortical neurons, the correlation coefficient is 0.951. So how long an animal yawns is an incredibly good predictor of the neuronal density in its cortex. So these findings really support the view that yawns serve this neurophysiological function. We've subsequently followed that work up looking at different types of taxonomic ranks, and we found that yawn duration is also really tightly correlated positively with brain weight within animals of a restricted taxonomic class here of felines. This was of wild cat species, a smaller sample, but similar positive correlations. And then most recently looking at the correlation between yawn duration and brain weight among members of a single species, but within domesticated dogs, that show this tremendous specific variability in brain size and body size. And again, these correlations hold up when we control for the size of the animal. So it's not that just larger animals in general with larger jaws have longer yawns, but rather it appears to be specifically tied to brain mass, and with that other sample more tightly tied with neuron density. And unfortunately, we just don't have those figures here for these species. So again, providing strong support that yawns do serve this neurophysiological function. Now, what is this function? Oxygen concentration in the blood. How many people have heard that we yawn to increase oxygen levels? Okay, this is by far and away the most widely viewed, public opinion, right? Unfortunately, there's no evidence to support that claim. Researchers have in fact studied this. Robert Provine, a pioneer in yawning research in the 80s, did really nice, elegant tests of this hypothesis where he altered the concentration of oxygen and CO2 inhaled by participants in the laboratory. And he found that neither manipulation had any impact whatsoever on yawn frequency. Moreover, he did manipulations that, for physical exercise to specifically modulate respiratory rates in participants. And he found that this had no effect on yawning frequency. And moreover, recent work in this area has shown that respiratory period actually increases following yawning. And if yawning is a mechanism to increase oxygen, we would expect the opposite effect to occur. So there's no support for this hypothesis, yet it persists, right? And we can understand why it persists. It makes intuitive sense because of this deep inhalation component that's accompanied by yawning. But to date, all the evidence suggests that yawning and respiration are operating under different mechanisms. Okay. So what does the data support? Well, again, some of Provine's work was suggestive that yawning might facilitate or function in promoting changes in state. Okay, activity to inactivity, inactivity to activity. We see that yawning often precedes major shifts in activity across species, sleeping waking cycles being most prominent. Also occurs in anticipation of important events and stressors. Okay, this is a figure of a paper looking at these circles are yawns, and the black bars represent activity, physical activity. And we see that yawns are often preceding changes in physical activity. So it does appear to be related to changes in state. Researchers have also examined how yawning might be associated with arousal. Now we can measure arousal in different ways. And it's associated with transient shifts in arousal if we measure it through EEG. And researchers also suggested that it increases neural activity at least through electrical measurements at the surface of the skull, or excuse me, the surface of the brain, through electrical cardiogram. So there's some evidence to suggest it might have this arousing function neurologically. So if state change and cortical arousal are the outcomes of yawning, which there's again some evidence to support, what is the neural mechanism that's driving that? Right? How do we get to changes in state and cortical arousal from a yawn? Well, yawning, again, I think it's important to think about its location. It's important to think about this action pattern and the way we view other similar physical movements. So yawns are more than just an extended, powerful stretching of muscle. But that is a major component of the action pattern of yawning. This extended gaping of the jaw is going to specifically modulate circulation into this region and likely increase blood flow to the skull, increasing arterial supply while also simultaneously increasing venous return. So, we have proposed that yawning might function primarily to enhance intracranial circulation and as a result modulate or alter the temperature of the brain. So circulatory effects are going to have corresponding thermoregulatory effects, particularly in species that maintain a constant, more or less constant brain and body temperature the way humans do, and mammals and bird species do. So this is the brain cooling hypothesis that I initially proposed. Basically, the hypothesis suggests that yawns serve as a brain cooling mechanism to increase blood flow to the skull, and by doing so, bring cooler arterial blood into the skull, removing hyperthermic blood away, which in turn could help facilitate arousal and state change. This could serve as the neural mechanism involved in these outcomes. Brain temperature is controlled by three variables: the rate of arterial blood flowing to the brain, the temperature of that blood flowing to the brain, and then any metabolic heat production that occurs within the brain due to mental processing. Yawning arguably certainly manipulates those first two variables. It increases blood flow to the brain. In addition, I'm going to argue, it can alter the temperature of the blood entering the brain. Yawning is also controlled by the hypothalamus, which regulates, among many other homeostatic functions, brain and body temperature. So, according to this hypothesis, yawning produces increased or enhanced blood flow to the skull due to that deep stretching of the jaw. In addition, has the potential to modulate the temperature of the arterial blood flow through countercurrent heat exchange. That respiratory component of the yawn might indeed have a function in its neurophysiological function aside from respiration. That deep inhalation of air brings cooler air into the oral and nasal cavities, which could subsequently cool blood in those regions that comes into close contact with arterial supply, so therefore has the potential to cool arterial blood to the brain through convection. In addition, the ventilation of the sinus system that occurs as a result of yawning, we have proposed might function or might promote evaporation of sinus mucosa that could again have cooling functions through convection. So this is the basic theoretical basis for cooling that yawning could produce. Okay? But we really need to see whether or not yawning is associated with brain temperature change. So we've measured this. Okay, so in this particular study, we had rats. We performed intracranial surgeries where we implanted thermocouple brain temperature probes into the prelimbic cortex of the rats. And these thermocouple probes could provide feedback on a tenth of a second basis of internal temperatures of the brain. So we could get continuous measurements of brain temperature while these animals were alive and moving about. And we were video recording these animals, and therefore we could pinpoint and sequence yawning events to any particular changes in brain temperature. And here's what we found. So this horizontal axis represents time before and after yawns, and these curves represent changes in brain temperature preceding and following yawning events. And we found that right before a yawn occurs, we see fairly rapid increases in brain temperature, on the order of about 0.12 degrees Celsius. And that following the execution of a yawn, the brain temperature changes begin to reverse. They peak just shortly after the yawn and then immediately begin to go back down to baseline levels. So these data suggest that yawning might indeed be triggered by these internal changes in temperature, and that the motor action pattern of yawning, promoting blood flow changes and countercurrent heat exchange, begins to alter that rise in temperature and produce temperature decreases thereafter. And these changes, these humps that occur around yawning events, were not observed during any other periods of the testing. And these changes, about 0.12 degrees Celsius, represent over 25% of the circadian variation in temperature that these animals will experience the entire day. So these are major shifts in brain temperature. This is some nice imagery, thermographic images from this work. In particular, we see hot spots. The eye and the ear are providing the hottest spots, not surprisingly, that we can detect from the surface of the skull. And again, we looked at changes before and after yawning events. And at time 0 is at the point of the yawn. We see that following yawning events, this is concha temperature, that's ear temperature, drops significantly. And in addition, cornea temperature, eye temperature drops also after yawning. And the magnitude of these changes, again, is detectable at the surface of the skull. Would this suggest this is a pretty widespread neurophysiologic change due to that increase in blood flow and arterial blood supply? We followed this work up in some animals that aren't really well noted for their yawning, but yawn pretty frequently. These are parakeets, budgerigars. They yawn about 3 times an hour. How many people had a parakeet in there? A few of you? Yeah, they're actually, population's wild down here in Florida. They're great to study for yawning because you put them on a perch and you can just point a camera at them and they'll just stare at the camera and yawn pretty regularly. So they're a good model species for this. We use thermographic imaging the same way that we did with the rats, different technology, different camera. But again, we looked at temperature changes at the hottest point, which is the cere right above it's a vascular tissue right above their beak. And we see that following yawning events, it's significantly lower. We looked at animals that did yawn and didn't yawn during these trials. The animals that were yawning most actually had more elevated temperatures during testing. Okay, again, supporting the fact that these animals, if they have elevated temperatures, yawning, if it's a cooling mechanism, we would expect it to be more present, more prominent. Yawn latency and yawn frequency were also tied to average temperatures measured at the cere. These animals run pretty hot. Okay, 42 degrees Celsius is quite a bit warmer than mammalian species. High metabolic rates. But animals that were running hotter during testing yawned sooner into testing and more frequently. Okay, again, supporting behavioral kind of measures to support that yawning might have a cooling function in these animals as well. In addition, we've studied our own species. Since I've started doing research on yawning, sometimes I get emails from people that have abnormal or unusual yawning symptoms. And they'll email me and they'll ask for advice and things like that. And there were two particular cases where independently 2 women contacted me with really, really similar symptoms of excessive and debilitating bouts of yawning. This is a video clip of one of the women that she independently sent to me in support of her case. These yawns are not voluntarily produced. She can predict the onset of these yawning attacks, and this is what occurs: just repetitive, excessive yawning. These attacks can last from 5 to 45 minutes in length, where she will just continuously yawn. She can't stop it. It produces dizziness and headaches. It's obviously debilitating to productivity and work. It's awkward in social settings. And she can have as many as 15 attacks a day. Okay? She had seen many physicians. The other individual did too. None of them could identify what the root cause of this was. But but in particular, she could predict the onset of these attacks. So what I said to her, I said, well, our research suggests this is related to brain temperature. If you could predict the onset, maybe you could just take your temperature before you're about to have an attack and also take it again afterwards. So she did. And this is what we found, that these attacks were actually preceded by slightly elevated temperature. So about 37.5 is a slightly elevated body temperature. I mean, everyone's a little bit different, but 37.0 is about 98.6. And that following the execution of these attacks, that was more of the temperature that was being recorded. So it's suggesting that these excessive yawning bouts were functioning in reducing temperature. At least they had that outcome. Okay? But thus far, these are all just kind of correlational studies showing that yawning is correlated with changes in either brain or cranial temperature. So we've also done some experimental work, manipulative work in the laboratory to see if we can specifically modulate the frequency of yawning through behavioral methods of brain cooling. And here are a couple. Nasal breathing. Repeated deep nasal inhalations have actually been shown to reduce temperature in the frontal lobe. Participants in the lab that breathe deeply through their nose show reduced yawning frequency. You can show them contagious yawning clips and they just don't yawn to them. Similarly, a manipulation that cools internal brain temperature is forehead cooling. Okay, applying cold compresses to the forehead have also been shown to reduce frontal lobe temperature. Participants that hold cold compresses to their head also don't yawn in laboratory settings to contagious stimuli. However, if they hold a room temperature pack or a warm temperature pack to their forehead, they yawn at rates that range from about 40% to 60% of participants will yawn in those circumstances. Okay, so now this is getting beyond just simple correlation. We can try and manipulate brain temperature, and we get predicted outcomes in yawn frequency. Most recently, we've coupled the thermal imaging technology with these attempts to manipulate cranial temperature. So this is some work I've done with Omar and some other collaborators. And basically, we tried to alter the temperature of the carotid blood supply by holding warm and cold and neutral compresses to the neck. And we used thermal imaging technology specifically designed for biological systems. And it would focus on the hot spot here. This is the medial canthal region in between the nose and the eye that has been identified as the brain temperature tunnel. It's apparently the best indicator of internal brain temperature, even better than tympanic. And what we found is that the temperature manipulations of the carotid did alter these measurements of these estimated measurements of brain temperature in predicted ways. Warm packs warmed this region, cold packs cooled this region. And subsequently, we examined how these warm and cold temperature packs modulated yawning. Warm temperature packs produced a higher, greater proportion of yawning in our sample. The new control is the neutral packs. The cold is obviously the cooler packs. Didn't change, this is the urge to yawn was higher in the warm packs. Didn't change the overall proportion significantly, although it's in the predicted stepwise trend. But if we look at mean yawn frequency, we see a nice effect here. The individuals holding cold packs to their carotid yawned more frequently than the cold pack condition, and it was even the case that there was a difference in the cold pack condition and the neutral condition. Again, consistent with what we'd expect if yawning is a cooling mechanism. So what this research suggests is that if yawning does have a thermoregulatory function and part of the cooling of yawning comes from countercurrent heat exchange, okay, that deep inhalation, if that does cool oral and nasal cavities, that it has an impact on convective cooling through arterial supply, then we should make pretty interesting predictions about how ambient temperature might modify yawning frequency. And this is a model that has been proposed. It's called the thermal window model for yawning. And basically what it suggests is, like other thermoregulatory behaviors, there should be a thermal neutral zone where the behavior occurs at relatively what we call baseline rates, right? Thermal neutral zone is what we're in right now. Okay, this temperature of this room is we call this room temperature somewhere between 68 and 72 degrees. We like room temperature because it feels comfortable. And it feels comfortable because we don't have to expend a lot of energy to maintain our 98.6 when the ambient temperature is like this. If it goes a little bit down, we have to expend energy to heat up. If it goes a little bit higher, we have to expend energy to cool. Okay, and when we do that, those mechanisms come into effect for warming and cooling mechanisms. So as temperature goes down, we should expect cooling mechanisms to diminish. As temperatures rise, however, we should expect those cooling mechanisms to initiate. But here's where we see perhaps a counterintuitive prediction, is that cooling mechanisms, in particular yawning, should diminish if ambient temperature reaches or exceeds brain and body temperature. Now, the reason I would expect yawning to diminish if at really elevated ambient temperatures is because the cooling component from the air would no longer be present. Taking a deep inhalation of air that is at or above one's brain and body temperature wouldn't have a cooling effect and might have the opposite effects, and yawning might be less frequent in these conditions. These specific predictions have been supported through lines of research in different non-human animal species, through a number of different experiments with budgerigars and these laboratory rats. We've shown that, in fact, initial rises in ambient temperature increase yawning frequency, but as temperatures continue to be elevated and approaching or exceeding body temperature, yawning diminishes. Similarly, we've examined or looked at the relationship between ambient temperature and yawn frequency in humans. And we've done this in two very distinct geographical regions, Vienna, Austria, and Tucson, Arizona. And we looked at the frequency of contagious yawning while outdoors during two distinct seasons in each one of these locations, summer and winter, where we recorded the average temperatures. 19.4 is Celsius is high 60s. 21.9 is low 70s, so it's right room temperature. So the summer in Vienna is about room temperature, and the winter in Tucson is about room temperature. But the summer in Tucson, 37.0, that's 98.6. And the winter, obviously, in Vienna is quite cold, around freezing. So we have some kind of overlapping temperatures in terms of the summer and winter, and then these extreme temperatures that only are represented in one geographic region. And here's what we found. We show that this interesting nonlinear relationship where yawning is most frequent, okay, at those intermediate room temperature ranges, okay, for contagious yawning frequency, but it's diminished in the winter, in the cold temperatures, and it's also diminished in the very warm temperatures in the summer of Tucson. Okay, consistent with the predictions of that model. And here's a scatter plot depicting the frequency of number of total yawns across all the participants in these two samples, and again shows this nonlinear relationship. So at temperature extremes, yawning is diminished. As far as I know, there's no other theory or hypothesis on the planet for yawning that would make these types of specific predictions about yawning diminishing when it's in the winter and it's cold, and in the summer when it's really hot. Okay? So this work on yawning and brain temperature has a lot of other kinds of applications, particularly related to health. Okay, frequent or abnormal yawning is often indicated as a symptom of a lot of different diseases and conditions, neurological conditions, central nervous system damage, epilepsy, multiple sclerosis. These are all accompanied by increases in both yawning and temperature, brain and core temperature. And then some other types of conditions that are associated with temperature decreases are also associated with suppression and yawning. Okay, so I think that understanding the neurophysiological function of yawning, at least being tied to thermoregulatory systems, is really, really important in medicine and pharmacology. So that is spontaneous yawning. Okay. Let's talk a little bit about contagious yawning. This is obviously a more interesting component, and we'll talk briefly here. Why is it that we yawn contagiously? Contagious yawning is widespread in humans. Okay, it's variable among individuals, but it's a phenomenon we're all certainly aware of. But it's not present in all species. So it's interesting. Contagious yawning is reliably triggered in some, in our own species in particular, but not observed in others. So what's going on here? To date, experimental evidence for contagious yawning, that is manipulating the frequency of contagious yawning in a laboratory setting, is limited to those species there. Human beings, chimpanzees, bonobos, domesticated dogs in response to human yawns, but not in response to other dog yawns. There's some evidence, or at least one paper suggesting a line of high-frequency yawning rats shows contagion, although I'm very skeptical of that paper. And then parakeets as well, the species I've studied, yawn in response to yawns of conspecifics as well in a laboratory setting. And this is a nice picture here of some research with chimpanzees. Are showing an iPhone recording of a chimpanzee yawning, producing a yawn in the observer. And then there's some observational evidence of contagion in a few other species as well. But what it suggests, this particularly the fact that birds, some birds show contagion, is that there's this convergent evolution, right? It's sparsely distributed. It's emerged independently in different lineages. This suggests, and I bet this list is far longer. It's just we haven't studied it, right? Species haven't been examined. Okay, so that's the kind of the phylogeny. The ontogeny of contagious yawning is really interesting. Human beings don't begin to yawn in response to the yawns of others until they're about 3 or 4 years old. Toddlers have been studied. They do not show contagious yawning. And it only emerges around this period of time and then is fairly stable. But interestingly, it also declines in later years. Contagious yawning goes down among geriatric populations. So again, has this nonlinear effect across the lifespan. Proximate mechanisms for yawn contagion, obviously sensory detection, seeing others yawn, hearing others yawn. In fact, we've done research where we've played audio clips of yawning to people, and it's a reliable trigger for yawn contagion as well. You don't need the visual stimulus. And even reading or thinking about yawning can elicit contagion in our own species. So we are very susceptible to yawn contagion. Now, what's the ultimate function? Now, this is where I think the study of spontaneous yawning is really, really important. I think it's a mistake to think about contagious yawning as being completely something separate from spontaneous yawning. The motor action pattern between spontaneous yawns and contagious yawns are indistinguishable. I could show you a video clip of a spontaneous yawn and a contagious yawn. You wouldn't be able to tell the difference. It's the same action pattern. It's just initiated by different triggers. So if it's the same action pattern, this deep, powerful gaping of the jaw, deep inhalation of air, etc., it should produce the same physiologic effects. Okay, so if spontaneous yawns increase blood flow to the brain, which is going to have a cooling function, spontaneous yawns might have those same effects as well. And therefore, the spreading of that behavior across the group might serve to enhance overall alertness, promote collective or coordinated state change and arousal, and maybe alter group vigilance. Okay? This is a working hypothesis. Okay? Alternatively, contagious yawning, that is, might not have a function. Okay? It may be a byproduct of adaptations in highly social species to pay attention to and respond to actions via state matching with conspecifics. Okay, so it could be that contagious yawning has no function whatsoever, but we're beginning to do some research examining the question of whether or not it does modulate group vigilance. So stay tuned, I guess, on that. And that's all I have for you today. I want to acknowledge the many collaborators and many people across the world that have contributed to the work, some of the work I presented to you today, including a long list of undergraduates, some funding sources, and I also want to thank you all very much for your attention.